Okay, all right, we are recording. So today we're going to talk about vector containers. We've all used vectors before, but we're going to spend the next 3 or 4 lectures on this very large topic called containers. Containers are vectors, strings, and many things that you may not have seen yet, and some things which we maybe talked about in Comp 220, for those of you who took Comp 220. If you haven't, this is a great introduction to algorithms and data structures. So we're going to explore all of the kind of containers, or pretty much all of them, that C++ has to offer because they're super powerful. And if you're building things like a Risk board game or an elaborate data structure for tracking electrical usage of electric cars or whatever, these are the kind of things you really want to think about and know about when you're building larger structures, because they just save you a lot of code, they've been debugged, etc. We'll also introduce our homework 3. So I know we're all finishing up homework 2. Homework 3 Connect 4. We'll just do a quick introduction to that today. And that will actually take advantage of a pattern vector of vectors, which some of you have used before, but we're going to start playing around with those since they're a little tricky when you first start using them. So it's just how to kind of combine data structures inside of other ones. So we got our quiz 2. Don't forget about that. It does not include templates, so you can kind of take a breather on that one. But everything else, all the way back through lecture 4, we got to have in there, and then our tic-tac-toe, of course, as well. And then we're going to have 2 labs this week. So we have a 2D vector of vectors today. So this is like nightmare situation. If you can handle lab 9, you can handle anything. It's going to be rows of kind of a 2D array, but where the rows are different sizes and they're random sizes. So it's just going to test your understanding of our lecture today. And then we'll switch over to a different container on Thursday called the list container, which, as you might guess, is a linked list. But good news is we don't have to like debug all the links and the pointers and everything. So that's going to be handled for us. Okay. So, and then we have our homework 3. I have actually all the links in Canvas now for Program IZ, Replit, and Program IZ Pro. In fact, I think you have to use Pro or Replit for this homework 3. So you got a little time to kind of figure that one out, but just a heads up there that might throw you a curveball if you haven't kind of tried Program IZ Pro yet. So we'll want to get over there. Grading reminders, just remember, if you're using dash or star in any of your logic, you really should be using the empty character data member of your class. So it's really tempting to be like, oh yeah, dashes are going to be my empty character. So don't do that in your logic test. Use your data member for your class. And of course, make sure that your constructor is initializing that data member. That's another nasty little bug that can sneak by you. So that's going to be how you're going to do that. And don't assume that X or O are the actual characters of your players. So when I run the unit tests, the automated tests, they're going to use lots of different characters. So if you find yourself making an assumption on that, you might want to see if you can find another way around. Usually this comes up in the isTie function. So just heads up on that. Okay. So all the usual stuff. Now, many of you are not having to use a makefile, but if you're really annoyed with this W error flag that keeps forcing you to use all your variables, you can edit the makefile in Replit and remove that W error flag, and those little warnings will go away. So, caveat emptor or whatever you say, warning, if you do remove the warnings, you might be the unexpected recipient of some nasty bugs. And if you do the AI bonus on tic-tac-toe, please let me know just so I can kind of go looking for your code. Otherwise, I'll assume that you're not doing it. But otherwise, give me a heads up on that. Look ahead to Connect 4. So Connect 4 is kind of a tic-tac-toe game, so it's going to be a little familiar. I've got the rules up on Canvas. Apologies that I haven't done that before on homework 2. I was a little behind on that, but the homework 3 has all of that in Canvas. You should be able to play this game online to get familiar with it if you haven't played it before. It's a little trickier determining if there's a win because the 4 in a row could happen at anywhere along a diagonal, horizontal, and vertical. So you're going to have to up your game a little bit on your logic when you're checking for continuity between 3 or between 4 of the same colors. Okay. So we'll have our prototypes as usual. So we'll have a .cpp file for Connect 4 and a .h for Connect 4. So the .h is your blueprints, and you're really just going to be implementing your methods and your constructor inside of your .cpp file. So the rest of it should be kind of done for you, okay? And instead of having a 3x3 array, we're going to have a vector of vectors. So your constructor has a little more work to do, and many of us will stumble on that. Today's lecture will introduce exactly how to get over that problem, but it takes a little bit of kind of adjusting to that idea, okay? And then we'll have more hints as we go along and in our labs just to get you ready for that stuff. But just remember that like tic-tac-toe, we're going to have to sweep across columns, we're going to have to sweep down the rows, and that, just because you have 4 blue things in a row does not mean it's a win. They have to be next to each other, okay? So if there's a gap between any one of them, then that's not a win. So a lot of folks will just count up the blues and go, hey, you won. But that wouldn't exactly be the case, okay? So, and writing an AI for this is actually a bit harder than doing it for tic-tac-toe. Again, for those who are interested, that will be a little bonus for you. You can score up to 15 points on that if you can manage to write an AI for that. But just checking for diagonal wins is kind of messy code, as some of you will see, because you do not want to be checking for a diagonal win below that point, right? Because you will crash, right? Because you don't have 4 things in a row. And so your loops, however you write them, need to stop before you reach out of bounds and crash your program. Okay, so keep those things in mind when you get there. That's usually where things get a little bit tough with that homework assignment. Okay, so today we're going to introduce these C++ containers, and they are kind of like that. We just want in C++ and any object-oriented language to be thinking in a encapsulated way. So encapsulation is kind of like these storage containers. As thinking about code, we just want to have all the messy stuff in the container, and then we want to have a nice interface where we just ask questions back and forth, like how many do you have? What's in position 12? And we don't really want to know what's going on inside of the containers. So that joke about sausage is, I don't want to know how they make the sausage. I just know it tastes good. So keep that in mind. We'll review a quick stuff we saw last time, and then we'll review, which most of us know about vectors, of course, but we'll just add a few more little hints of new things, and that will set us up for dealing with our other containers, because many containers support the same methods that vectors do and that strings do. So not all methods, but things like erase and clear have similar meanings across all the different kind of containers that we're going to use. And that's really nice. So if you learn it on vectors, you now know a little bit about how to deal with them on these other containers. One of those things is called iterators, and many languages have a concept called an iterator. This one is kind of weird. It's a very abstract concept. It's like, hey, I got a container with a bunch of stuff. I'm not going to tell you how I'm organizing it, but when you ask me for the next one and the next one and the next one, I'll just give you a carrot, right? So an iterator would be like, just give me the next one. I don't know how you're organizing it, but I want the next one and the next one and the next one. So we will see that containers have a common concept called iterators. And in fact, it's something that every modern programming language has. Python has it, Java has it, JavaScript has it. So the idea of an iterator is the most important thing. We'll also introduce a new type called auto. Auto is our friend. It saves us from needing to remember a lot of detailed syntax. And sometimes it doesn't work for us, but we'll kind of give ourselves a break and be using auto with our iterators just to give everybody a little more breathing room when we're learning this stuff. Okay, so that's predominantly all we're going to cover. It's not a lot, actually. but it is some new concepts. So let's just real quick touch on the template stuff from last time. Remember that all we're doing is copy pasting. Anywhere I see a Q, I'm replacing it with whatever type is between those things. So if you imagine the whole vector library is a lot of code with a whole lot of Qs in it, right? There's actually no executable C++ code in the vector library. It has to be replaced with all the data types. Otherwise, it will never compile. So that's really what our preprocessor is doing with that little template hint over here, is going to replace all that stuff for us. Okay. So same with classes, same kind of thing. Wherever you see a Q or whatever the template name is, we just replace that with the data type. And it really is just that simple. But sometimes it's hard when we look at code like that to force our brains to see what's going on there. We're pouring in a data type just like we might be pouring into arguments. Okay. So think about that when we're using the vector. It might help you get to more comfort with it when you write your own templatized functions and classes. Okay. Now, last time we talked about library design. I'm not going to go into this in much detail, but I would like to point out that if you are using include guards, in particular this one here, this one should really surround everything in your .h file. Okay. So don't like put your pound vector stuff up here or some other .h file outside of this. I don't think too many of us were doing it. And most of the time, some of the time you can get away with it, but put everything inside of there. That way, if it turns out that we have defined something, then all this stuff just won't happen, right? So we don't have to worry about things showing up multiple times, which is what ends up crashing for us. Okay. So those are our include guards. And of course, you can use the pragma ones that everybody or many people were actually using as well. Okay. Okay, so let's dive into some new stuff. So we introduced this briefly. As you all remember, the constructor initializer list is a way of initializing your members of a class. Sometimes constructors want to call other constructors, but we have to put them on the same line with the constructor initializer list. So here's the problem we're trying to fix. Somebody says, hey, I want a class A, and I want a default where all of the data members are 0. And I want that to be my default constructor. Okay, that's just fine, right? That's the good old-fashioned way of doing it. But I also want another constructor where I just want to specify the Z value, okay? So we all know we can kind of use the constructor initializer list to solve this problem. But let's just say we're looking at this and we're thinking, can't this one of these call the other one, right? It's really tempting to try to call the other constructor from inside of the curly braces. But for a number of reasons, we're not allowed to do that. So here's a couple ways we can solve this problem. So first off, we could extract all of that duplicate code and put it in a little private function inside of the class. So I could say, I'm going to call that my initialization function. And then I'm going to call it from over here. And then I'll call it from over here. And I'll also set the Z value while I'm at it. Okay. So now at least we have one set of code. And instead of having bugs in 2 places, maybe I only have bug in 1 place, right? So that is always our goal, is to not write the same code twice. So that's going in the right direction. Okay. But we could do this a different way as well. Okay. But that's really not a terrible idea. And sometimes I do write constructors that way. I just create a separate function that I call at various times, right? And that's okay. The delegate constructor solves that problem a little more elegantly. So here is our kind of fully defaulted base constructor. And here's a constructor that is calling the delegate constructor alone, and then after that happens, it overrides the Z value. So that's another way of doing it. And this is what we call a delegate constructor, okay? And many of us have unfortunately discovered in this class over time that if we do this down here as a function call, if we don't get an error, we are probably going to get some very unpredictable behavior, and it's a nasty bug. Okay, so we really don't want to do that. We want to use our constructor or our delegate constructor over here. Okay, and we might also have our constructor initializer list out here for some other stuff, right? But this is always going to happen first, and then anything else we put on that line will happen after. Okay, so that is just called a delegate constructor, and you might find that to be a useful thing in some of the things that you're doing. We'll practice that here in just a second. Okay, but it's going to call and construct this one. So if I put a C out message here, I'd see this one trigger first, and then I would see this trigger second. So the order is you first, then I'll take care of what I got to do over here. Okay. And that's perfectly fine. So we'll see that in a couple different areas, I think. Okay. So if we wanted to, for example, solve our tic-tac-toe constructor using a delegate constructor, we could do that. We could say our first constructor is just going to call the other constructor as a delegate constructor with a specified dash default for the empty space, right? So, and then we implement our explicit constructor over here, and that's just fine, okay? So that would be okay. Of course, we could also just say equals, right? Single quote dash, and get rid of all this stuff up here. So this is a simpler case you could do in two different ways here, right? But this is just an example of how the delegate constructor could fit into that situation, okay? And adding couts to your constructor, especially when you start doing piggybacking like this, is a very helpful thing when you start getting crash bugs and you're confused about errors and stuff like that. Just a couple couts can help you know what's happening there. Okay. And there's how, that thing gets initialized. We call that constructor, goes into the empty token, and then we go back. So let's just do a real quick one here. Click on one of these links below. We've got a program IZ link and we've got a replit link. So this is a poker game with a private constructor, and then we want to have a second constructor and piggyback or have that delegate constructor call, okay? So the second constructor is going to initialize all the private values by calling the poker constructor as a delegate constructor, okay? And then we should be able to modify num players as a class in our new constructor, okay? And then you should be able to call it for main. I think all the main stuff is kind of set up for you, okay? So bopping over here, here's our default constructor, right, over here. So we want to create a second constructor that allows us to call the first one. So it's going to be poker, right, like that. This, and I think we're supposed to have some number of, let's take a look in main. So we want to be able to specify how many players. So I'll just say int p like that, call my delegate constructor poker, no arguments, right? And then down here, we'll have our curly braces for our constructor, for everything. And we can overload that. Oops, that's inside of a comment there. Sorry about that. So we'll put it down here. So we can do this inside of the body of the function if we want, or we can use a constructor initializer list. So let's just say num players equal p, right? And see if I got lucky and everything compiles. And it did, right? So that is just one way to do that, okay? So, and again, you can, document your constructor calling order by putting little cout statements here and in here just to help you debug things if you need to. Okay. Okay, but that's our constructor delegate. Okay. Questions on that one? This is sample code if you need to see that. Okay. Now, if you do decide to, go whole hog and put your constructor initializer this, make sure you put your delegate constructor call first, and then do something like num players parenthesis num p, right? So this is our constructor initializer list following the delegate, right? So it goes after that delegate constructor. And then you wouldn't need that inside of here, okay, if you wanted to do it that way, okay? Okay, so two ways to get that one done. Okay, let's talk about containers because that is our big topic for the day. Basics, right? So when I create a container, I fill it with stuff. So I'm using C here to refer to a generic container that could contain anything, but here we're obviously filling it with integers, right? So when we create the container, the important thing to remember is it's empty. It's not like an array, and most of us know that, and we push back things or we do stuff to get stuff in there. And then we can always check for the size. All containers have a dot size method. That's really nice. So you can always tell how many things are in there. Now, they also have this thing called capacity, and this gets at their secret life. Containers have kind of this secret life where they are waiting and ready for more things to be added. And rather than constantly reallocating space, like some of us might remember from algorithms class, they kind of are getting ready for you to, maybe use up more space than you ask for. So they kind of default to a certain size called the capacity, but their dot size is how many things we've put in there, okay? So that hints at their underlying data structure a bit. It means, yeah, they got some more space they've allocated ahead of time, okay? And of course, all of our containers are going to use templates, but they come in two kinds. Sequential is, you think of it as you as a programmer decide the order in which things go in, okay? So a vector is a sequential container, a string is a sequential container. A map or a dictionary for Python-y folks, or a hash table for algorithms folks, is an associative container. It doesn't go necessarily in the order we put stuff in it. It has its own rules about how and whether it will organize the stuff inside of it. So we call that associative, okay? And we can, of course, package these things inside of each other, which is really, really cool and powerful, okay? So we'll start with our vectors, and it'll be a little bit of review, but all of these concepts are really going to apply to all of the containers that we explore over the next couple of weeks, okay? And in particular, vectors is something you're going to need for Connect 4, which is our homework 3, okay? So we put stuff in there, right? Usually we'll use a pushback. There are insertion operators that give us random access. So random access just means I can put any number I want in there and pull something out, unlike a linked list, right? If I ask you for something in the linked list, you have to go walking down the linked list to actually get there, right? So random access means that we can efficiently pull stuff out. Another container we're going to see is called a deck, but it's really a double-ended queue. So if you think a little bit about some of our linked list stuff we did, again, algorithms folks might think of pointers to the tail and pointers to the head. That's a deck. So we'll play with that. We'll play with a doubly linked list, which is another flavor of a linked list, and a singly linked list. So these are all containers that are in this standard set of containers, and we refer to them as sequential, right? But the underlying data structure is different for each one of these, so they have different performance. So if you're building a really, really, really big thing that you need to jump around and have square brackets in, you're going to want to pick something from this suite of tools that's going to be really efficient for that, okay? So that's why we have all these different flavors. And we even have a smarter array. So unlike our old-fashioned array, there is a container called array. And so we will look at that as well, okay? So that one is not quite as flexible as some of these other ones, but it's better than the old-fashioned one that we've been using. And of course, our old friend, the string, which we've used since the very beginning for most of us who have been coding. Now, on the associative container side, we'll come back to these after a couple lectures, but for folks who took algorithms, you'll remember this stuff as binary trees and hash tables. So, and we'll make that connection when we get into these. But basically, these are dictionaries or some kind of a dictionary kind of structure that allows us to offer a key like word and get a definition out of the dictionary back. And they're super, super powerful. You can build databases and things with these if you really want to in memory. And so it's really good to understand how to use these things, okay? But let's take a look at our first container, which is vector. And the primary methods, pushback, clear, at, square brackets, and size. So we'll review these briefly. But remember that when we create something, it has nothing. It has capacity, but as we don't really know about that so much unless we ask. It's like a little reserve space in case we're going to add 3 or 4 or 5 things. Um, and same thing for any other data type. This is going to hold characters. We haven't put anything in there yet. Pushing back something puts a copy of that thing in there. So there's a 10 over here, so to speak, and now I have a copy of a 10 over here. This 10 is still sitting here, right? It hasn't changed any. So we say we put in copies, and that's our size of our container, okay? Same for our characters, right? Same thing, dot size, okay? And of course, I can change what's at square bracket 0, 10, or at parentheses 1. Both of those are doing the same thing. This is an overloaded operator, just like our overloaded plus in our number class. So the vector is not an array. It does not know how to count naturally. So whoever developed the vector class had to overload the square bracket operator to make it act like an array, okay? So it's like, oh, okay, so it's really not an array. So, but there's a slight behavior difference between this, we'll talk about in a second, and this one here. This one has airbags like your car. This one does not. So if you do something bad over here, you're just going to corrupt memory. And if you do something bad over here, it's going to actually quit your program and be like, oops, you did something dangerous, okay? So you can use both of those things if you want, right? But they're going to have maybe different impacts on your error handling, okay? So VC0 gets 10, VC, and this is an equivalent. Sorry, I was talking about this in terms of a comparison, but of course, if you're comparing something that doesn't exist, you can also get a crash there, okay? So we're still just comparing to that location. Now, VC clear or VI clear is going to get rid of what's inside of VI, okay? So now our size effectively has gone to 0 on those two things, okay? Okay, so those are our basics for like erasing everything inside of there and comparing things. Just remember that we're pushing back copies of stuff, okay? Remember that truism about pushback, okay? So now, when we do something like this, right? So if we say VC clear, we're good. If I say, hey, what's at position 1 after I do a clear, we're going to get an exception, which is another way for saying controlled crash, okay? Our program's going to stop and we're not going to continue because that thing no longer exists, okay? Now, if you decide that you like square brackets better, you won't crash. You will just corrupt memory, okay? Or you may pull out some garbage data, okay? So square brackets are okay and fine, but if your program is crashing or you're uncomfortable with how stable your code is, switch back to .at. It has a little performance problem, not problem, but cost. But it's not like in this class, you're going to really have to worry about that so much. So if you're a little bit queasy about some of the stuff we're going to write in our homeworks, just go all out with the .at. And I guarantee you, you'll find out earlier than, the folks not using it if you've got some problems in your code, okay? So it's going to allow us to kind of determine that sooner than later, okay? So here's just, side by side, no big surprises there. I think we've all seen that stuff before, okay? So, and you can ask yourself, hypothetical question, would you rather crash or have corrupted data, right? Most people would rather know while they're coding that their code has a problem than after they ship the code. So that's why we kind of do that. Okay? Now in memory, you might just be curious to know what is going on with a vector. Now we don't really need to know. That's the whole idea. And in fact, different compilers are allowed to implement vectors however they want. So if I'm using a compiler called the Clang compiler, it might implement the hidden data structure one way, and some other compiler on an Arduino processor might do it completely differently, because maybe on an Arduino processor, the compiler is, really, really focused on memory, right? And so it's going to be trying to do something more efficiently. So it's always going to be different, but the point is we don't care, right? Well, we don't really care. We just want to deal with the interface. But here's an example of what could be happening. There could be a hidden pointer as a private data member of the vector class. and it might be templatized, right? We kind of did a little exercise like this. And when I push back something, it might be dynamically allocating an instance of that something and then hooking its pointers up. And then if I erase it or I, insert something, it's got to do all the messy work, right? That's like a lot of code that we obviously don't have to write. And the good people who wrote that spent a lot of time thinking hard about how to make that as optimal as possible. So there's a lot going on underneath the surface. And fortunately, we can most often just trust that it's doing the right thing once we decide that a vector is the right uh, container for us to use. Okay. But it is interesting to realize that there's a lot going on under the surface. And guess what? There's an array down there, right? There's really no way around using arrays. So there's no magic flexible data structure that, spans our silicon and our phones and our processors. It's still an array at the end of the day. It's just that the vector class is hiding all that messy stuff from us. So we can think of it like a vector, right? So it's very similar, right? The problem is that, it is going to be empty until we put stuff in it. So it's not exactly like an array when we allocate it. And also, like we just said, it's not like the 1, the 2, and the 3 are necessarily even next to each other in memory. Some array implementations might have, or vector implementations might have like layer 1, layer 2, right? We don't know if these things are literally next to each other. So I can't add a jump in memory from the 2 position of a vector and necessarily get to the 3. I can do that with an array. I know that the 3 is going to be stored right next door, but I really don't necessarily know that with the vector. The vector is masquerading as an array for us. Okay. So, and most of the time that's perfectly fine. Okay. We use those overloaded operators or that at method to sort of get something quote unquote at a particular position. Okay. So a little bit about our lower memory management. We don't have to worry about too much, but let's play around with this just real quick. Let's initialize a vector of a certain size and store values 0 through 19 in 20 locations. So you're going to need a loop. You're just going to count 0 through 19 and store some values in there. Okay. And just store the index value in there. And then try the resize. This is an important lesson here. So when you resize that thing to half of its current size, print the contents out again, just for the valid portions of that thing. And then resize it again back up again and see what happens to memory. Okay. So it's important to see the difference here because arrays, of course, behave a little bit differently. Okay. So I'm not going to do all the code, but let me just pop this up so you have some inspiration here. Right. So kind of go ahead and define a vector, and it's going to be empty, right? And then you're going to have a for loop, and then you're going to have another for loop to print that thing out, and then we'll do the resize. Okay. So I'll flip on over to the solution so you have some code to look at, but if you know what you're doing, feel free to just jump ahead, right? But homework 3, this will help you a little bit with that, right? So we got for loop for pushing back some values, okay? And if you wanted to, you could just say equals curly braces, 1, 2, 3, 4, 5, 6, 7, 8, 9, 20, right? Out here. But we're going to use a loop for that, okay? And then we print it out. Notice, of course, we're using the dot size. Right? You could put a 20 in there, but it's much better practice to start now. Just don't trust anybody except what the vector says its size is, okay? Once you know it's been filled up, okay? So you should get that stuff printed out there, okay? And then you can resize to half its size. So we're going to chop it in half, throwing away some data, of course. Then print again by its current size. So it's now going to know that its size has been dropped in half. So you don't even have to think about what the math is for that, right? And if you push it back up again, it's going to make a decision to fill in with zeros. Okay, so it's not like we're going to get that data back. It's going to reinitialize that to some default value. And so remembering, what the default value is for all of these different methods is a little bit maddening. No one's going to expect you to memorize that. But as coders, you should be aware, of course, that that behavior could be unpredictable. So you should always test and read up and see what is actually going to happen there. Okay. So just a little bit of about, what's going on with reinitialization of that space. Okay. So let's talk about rows and columns. So I kind of hammered this into everybody's heads in Comp 130 for those of you who took that from me. So I always talk about rows and columns, and I will be pretty consistent about it in this class. So this is an empty vector of integers. You could think of that, if you want to, as a row, or you could think of it as a column. For the moment, let's think about that maybe as a column, although I always talk about it as if it's a row, okay? So there's this vector of integers with nothing in it. It's got some reserve capacity, but probably it's going to have to outgrow that at some point, right? And here's an empty one. So this is what we have when we say vector of int. So this is a vector called VVI, and what does it hold? It holds rows of information, okay? So each thing inside of the vector is itself a vector of integers. So the type of the outer vector is vector int, and the type of the row is int. Okay, it's a vector of integers. Okay, and you can, these days you can leave no gap in there, but just if your eye might become confused, but I don't think the compiler will anymore. But when those two things come together, they look like a stream operator, but you can leave them without a gap if you want. So here's our other vector of characters. No rows yet, right? But that's what the row type is going to be. So if you're ever confused, just kind of work from the inside out like we always do. Vector of int is the row, and vector of char is the row there when we fill it up, right? But there are no rows yet, right? So what we're saying here is we got no rows yet. We don't even have anything to put in an empty row. Like we don't even have an empty row. We need to have an empty row before we can even put anything in that row. Okay, so we don't have any rows. Okay, so we're going to need to put in an empty row, and then we're going to have to fill up that row. You can't just start throwing things in a vector without having a row to put them in. Okay, so that's going to come back to haunt us here in just a minute or two. So here's a couple other things. So let's look at this code. Here's two vectors, v integer a, vector integer b. Okay, so then we got this row, empty row of integer vectors. Okay, so there's our empty thing. Now, if I say VVI pushback VIA, I will always remind you that pushback puts a copy, always, 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 always. So it's going to make a copy of that 10, 9 vector. So it's not connected to VIA. It's our first row in there with 10 and a 9. And if I put the VB in there, VIB now, the 1 and the 23 are in there. But they are in no way connected to VIA and VIB, okay? So if I come back and I add, well, first of all, just add a third row, notice it is a different size. That is perfectly fine. There's nothing preventing us from having rows of different sizes in a vector. That's an advantage over the actual 2D array that we used in tic-tac-toe, okay? But if I clear VVI1, right, I've just eliminated the contents of VVI position 1, okay? So I haven't got rid of the row, because then I would only have 2 rows left if I could do such a thing, right? So I've just cleared specifically VVI1. If you say VVI.clear, you're getting rid of the whole thing, okay? So I'm getting rid of just row position number 1, okay? So keep that one in mind, okay? Okay, that one right there. So we can always come back and fill stuff in. So let's take a look at a couple other examples. Here we go. So we got our kind of gap there just for clarity, but again, you can skip that. So I'm going to put an empty vector inside of VVI. Okay. Now I have row 0. So now I can put things in it if I want. But what am I doing? Okay, so VVIA, VIA, pushback 10 and 9. Notice those are not connected. I know I've kind of said this, but like that's not going to change what's going on in here because they're not in any way connected, right? So this is just a separate thing altogether. But I can put a copy of something in there, right? Which was empty, right? And even if I change the VIB, of course, it's not going to change my rows. But at some point, I'm going to come back and probably fill these guys up by pushing something into each one of these, okay? Okay. And this is just me creating a third row. Okay. So the size of VVI right now is what? What's the size of that thing, right? So if I say VVI.size, I'm going to get how many things the outer vector has, which is 3, right? The size of VVI is the number of rows, always, always, always. The size of VVI square bracket 0 is the number of things, of course, in that row, which could be a crash if I don't have a row 0, or it could be 0 if this thing's empty, or it could be a million, right? It really depends on what our code was that we executed already. Okay? So these are just kind of the basics about working with these 2D vectors, okay? So just keep in mind that, when I see these square brackets, I've picked a particular row, and now I'm pushing something into that row, right? If I'm doing it up here, I haven't got any square brackets, so I'm creating a brand new row, okay? So we'll see this in code here plenty going forward, okay? So there's my basics. And we're always pushing a copy. Whatever we put in those parentheses gets copied, right? So let's try to create a vector of characters. And there's a new kind of insight into this. So without using a for loop, okay? Let's not use a for loop on this. Create a row with A's, B's, and C's, right? So 1A, 2B's, 3C's, separate rows in a 2D vector of vectors of type char, and then print that thing, okay? Really, really simple, right? Now, instead of using pushback 3 times, which you're welcome to do, like you could do pushback, pushback, pushback. That's perfectly fine. Or you could use this very cool curly brace format and let C++ figure it out. So in other words, this curly brace could be filled up with 2 B's in here, right? So when I say, hey, push back this thing, C++ goes, oh, that's a row, and we're a row of characters. Okay, that's a vector of characters, and it will just automatically construct that for you, okay? So let me show you what I'm talking about, but you guys should try this, right? Here's our vector of a vector of characters. I'm going to push back an entire vector with the A in there. Now, many, many people will try this. And on a typical day, there's every chance that I might make this mistake too. I'll be like, oh, I'm really excited to put in my first row. Well, if I do that, I'm going to get a crash or a compiler. It's going to say, hey, you can't put a character in there. I need a vector, right? I need a vector. So putting these curly braces around there says, oh, C++, you figure it out. You look at what kind of vector that is, turn that into one of those things. And that's really handy as a coder goes, right? So now we've got a row of B's and a row of C's, okay? How do we know what that is? We got to kind of think, okay, if this is a vector of something, then this is that something. And if it doesn't work, like if you put curly braces, 1.0, 2.0, 3.0, then you're going to have a compiler error, right? So it's got to be the right type. But otherwise, it will figure it out and create a vector for you. Okay? The next part, when we print these out, we're going to need our double loop, rows and columns, right? Always rows on the outside of our for loop. Well, not always, but standard, right? So when we're printing, if we want to kind of stick with the row column paradigm. We'll go R's on the outside, C's on the inside. But notice what we're doing here is we're checking the size of row R, okay? So the outer loop is the number of rows in VVC, and the inner loop is how wide is row R for this value of R, 0, 1, 2, 3, 4, okay? You don't want to assume that that thing is perfectly square because, as we'll see in our lab today, it's not going to be square, it's going to be random, okay? So think about that, okay? And then, of course, we just print out each RC as we move across each row, okay? And then ENDL outside of the loop, right? So just make sure that kind of jives with you. And if you try to do this, you'll get a crash, of course, or you'll get corrupted data, right? If you try to use that in here, right? So that's going to be an important difference. Questions on that one? Okay. So all of our two-dimensional data structures will probably be dealing with vectors going forward. So this is a really important concept. Let's try another one. This was just kind of a little mathy. So we want to fill up a 20 by 20 grid of numbers that in sequence go from 0 to 399. That's 400 numbers. And try to get them so they increase monotonically, right, across the rows. So there's a couple ways we can do this. I'll show you both, but it's good practice. And then we want to print that grid, okay? The surprise here is, of course, you need to create the empty row before you can fill it up, okay? Now, whenever I'm doing stuff like this, I first put in some junk data, and then I come back and figure out what the data should be. Because getting the rows built is usually the first part of my construction job. And then it's like, okay, what are those supposed to be? So you could push back R times 20 plus C, and that will give you a way of like filling this thing up, okay? So here's that first method, okay? R equals 0 to 20, push back an empty row. So this is the part that often gets forgotten and causes crash problems in homework 3, okay? So we got to create the empty row before we can fill it. And everybody will say, I don't know why it's crashing, right? If I didn't do this, it's like, why isn't it crashing? And I'll be like, well, you don't have a row R. There is no row. Like this thing has no rows, right? So we got to put a row in before we go across that particular row and fill it up, okay? So that creates the row R, and then we can, put something into row R, okay? But that part has to come first, okay? If we don't do that, we just kind of crash. And then our kind of familiar format for, just printing stuff out, okay? Use the VVI square bracket R dot size for that particular row. Which you could say, oh, well, I know it's 20, so I'll just use 20, but it's much better practice to trust the vector to get that information out, okay? Now, some of you will be wondering, well, if I can do this in 2 dimensions, can I do it in 3 dimensions? And yes, but we won't do this. This could be a whole other vector. So you can go as deep as you like. You can go to the 4th and 5th and 6th dimension if you want, right? So you can have some pretty wild data structures in there, and that stuff will all hold up. Now, here's my favorite, and you guys might remember this from our elephant lab, Comp 130. So you can, in a for loop, have 2 index values, int R and int count, right? All kind of just one data type, 2 variables. That's kind of not used very often. And then every time you push something back, after the count gets pushed back, we post increments, okay? So remember our pre and post plus plus. That means, hey, put back a copy of count and then apply the increment after the count gets pushed into the vector, okay? Sneaky little way of just updating every time we make an assignment, okay? If you put it before and you said plus plus count, you'd kind of be off by 1, right? You wouldn't get the 0, 1, 2, 3, 4, 5, etc. You get something else, okay? And don't forget the empty row part there. We got to add that empty row. And then we can kind of come back and just use our standard for loop to print that thing out. Okay. So this is a great way to kind of pull data out of a flat array, like your initialization for your tic-tac-toe count, right? Some of you probably did that already. Okay. Questions on that one? Okay, all right. So the error, of course, would be if we did not push that thing back, right? And so we kind of talked about that. That's just going to crash because there is no row, right? We don't have a row to put stuff into. So, and this is always mystifying to people. It's like, why am I getting a crash there in zero when R is 0? And it's like, well, we just don't have a row yet. We got to add that, okay? If we didn't do that part, okay? Okay, so I'm trying to remember why this one's interesting. It seems a little bit obtuse, but I don't think you got to write all this code. But let's say we wanted to put the prime numbers in here. It could be anything, right? So I just picked on prime numbers. So here's our prime numbers. So we want, the purple ones in row 0, the orange ones in the middle, and these other ones there. And then we want to erase row number 1, okay? So, but we're clearing the content. So clear is a very specific meaning. So notice what happens there. That is not eliminating the row if we do that. If we say VVI square bracket 1 dot clear, we're clearing the contents, not erasing the row. This will also cause some problems for folks down the line. Okay, it's just a conceptual realization. Clearing clears the contents of that specific thing. Okay, so this just illustrates that. So give this a try. Just sort of, I'll put the code up there for this. But if you want to really clear the rows of VVI, you just say VVI dot clear, and now you blow away everything, right? So remember to check your dot sizes in case somebody has done something like that, right? So if you clear row 1, now if you don't check the size, you're going to probably get a crash, right? So here's kind of a learning moment if you haven't been doing that, right? So we'll have one fewer, well, we won't have any, we'll have a 0 size, right, on the row number 1. So we won't print anything at all for that. So you should get a blank row as a result of that for row equals 1 there. Okay. And for those of you who may have forgotten, remember our for loops, we get a free ride for one statement. So this is the free ride for that loop, right? And notice that I got curly braces here, okay? So as soon as this is done, we terminate the line and then we wrap around and do the next one, okay? So I've just saved myself a couple extra lines of code here by taking advantage of that fact, okay? But you can add the extra curly braces in there if you want to, okay? But that sometimes I'll leave that stuff out, okay? Okay. Okay, let's talk about this weird thing called iterators. This might be the only really tricky part of this lecture. So an iterator is just something, you can think of it like a pointer that just moves over an ice cube tray. I like the ice cube tray analogy for things that store stuff. So the bummer is its data type is god awful, like vector, less than int, less greater than double colon iterator, the word iterator, then the variable name q. So that's like saying, hey, q is a pointer for containers. Okay, what kind of container? A vector integer container. Well, why do we need a pointer? Like, why do we need this special pointer type? Can't we just like have a pointer? Well, vectors aren't arrays, so I can't jump to the next storage location by just adding 1 to Q if it's a pointer. So we have to invent this new data type that's kind of strange that is like a pointer for vectors. And that's its big, messy data type, okay? That's like a thing that counts positions in a vector. And call it whatever you want, Q, I, X. I tend to use Q in this class just for consistency, but you can call it whatever you want, okay? So if I have a vector of 8 things and it's this container, right? We got some handy methods. I can say vec.begin. That's going to give me the 1, okay? Or not the 1. It's going to give me the position of the first container or the first storage location. Vec.end is a strange thing. It's something that doesn't store data. It's like the bumper at the end of a train track. So when we're iterating through a container like this, if we're not using position 0, position 1, we'll see here in a minute, we can keep going until we run into that bumper, that vec.end bumper, okay? You're probably all thinking, I hate this already. Can I just use square brackets? Yes, you can use square brackets, but not all containers support square brackets. So it's good to just sort of play around with it on the vector while we can do that. So vec begin is like a pointer. It doesn't give me the number 1. It gives me the location where I can go find the number 1, right? So that's kind of like a pointer, but it's this pretend idea of a pointer. So I can do something like this. For Q equals vec begin, continue while Q is not equal to vec end. So it looks like a regular for loop for a pointer, sort of, but there are no pointers here. So this is all a lot of pretend of these vectors sort of making themselves look like arrays. Okay, so if we think of it like a pointer, it's a little easier to deal with, but it is a little bit more syntax. So similarly, if I want to know what's at that location, just like a real pointer, the vector offers an overloaded star or dereference character. So if we remember our pointer syntax, we can assume that the vector is masquerading like a pointer with its iterators. So star Q means give me what's at Q, even though Q is not really a pointer, it's an iterator, okay? So star Q, if Q is set to vec begin, will give me the 1, of course, right? And so now I can iterate Q and it'll act like a pointer. And again, I'm sure everybody's like, I want the square brackets back, right? It's way more intuitive to do the square bracket, but let's do some code. So here is a Q. It's kind of like saying int x, but it's a pointer kind of thing. There's my vector, right? Vec. So for something, this big messy thing up here, Q equals vec begin, semicolon, continue while Q is not run into the bumper on my container, Q plus plus. So even the plus plus is overloaded here. It's like, what does that mean? I don't know. The iterator class has overloaded the meaning of that to mean move to the next thing, wherever it is. We don't know how this thing's storing the data, but the iterator kind of abstracts that away from us so we don't have to worry about it. So it's just going to the next thing, whatever that means, right? So if I dereference Q at any single time, I can figure out what's at that location on the iterator, okay? Now, if we get to the bumper, that means don't try to look at the pointer because you're going to crash, right? We can't dereference a pointer that looks at vec end. So our for loop will actually quit before we do that, okay? So this is the universal way we can go through containers of anything, whether it's a vector, a string, a list. So once you learn how to write code this way, it really doesn't matter what you're dealing with. You can just iterate over the top of it, okay? But it also shows us a really interesting code pattern which exists in many languages. It's like, hey, let's come up with this generalized concept of a thing called an iterator. And trust me, it doesn't ever go away. It's out there everywhere. So an iterator is something that iterates over the top of collections of things, okay? Until we hit a bumper of some kind, okay? So we don't use less than or equal to with iterators. We say, you know, as long as I'm not equal to. That's probably the safest thing that we can do in this class, okay? And you'll see later on why I say that. But You just kind of hang on to that not equal to, right? So it's a nice generic way to kind of go over the top of something without square brackets, okay? Because not everybody supports square brackets, okay? And we'll see that as we go forward, okay? We can also do math with these iterators. I can say, hey, jump by 2, right? So Q equals Q plus 2 is legal because even though it's not a pointer, the iterator class knows what to do with that. It's like, oh, you want to go to the next thing. Okay, fine, right? So we get to do familiar things like that to jump to the next and the next and the next, okay? Even though these things might be stored in some crazy random storage stuff, we don't need to care about that too much. The other thing is we can go backwards, right? We can subtract from the Q, of course, and go in the opposite direction, okay? So let's look at some actual code. So for int I equals 0, right? We could also say, so this is like just doing it the old-fashioned way, right? The way we've come to love and, you know, feel comfortable with. This is us doing it the new modern way, which is annoying because there's a lot of syntax there, right? And notice the not equal to there, okay? And this is thank you auto. So auto is a automatic data type figure outer. It says, oh, what would Q be based on this? It's like, oh, well, begin gives me a vector iterator for integer because I know it's an int vector. Therefore, it will automatically fill that in for us. So in this class, just because it's just a little too much, we're going to use the auto rather than this syntax right here. But you're welcome to use this syntax to test it out, right? It's just sometimes a little error prone, okay? So it's killer app, meaning, you know, it's awesome for when you're doing iterators. For auto, Q equals, vec begin, off we go, okay? And in more and more modern code, you're starting to see auto all over the place, which is sometimes good and sometimes not so good. But let's try it, okay? So let's print out the contents of the vector in those 3 ways. First, just warm yourself up using the square brackets, right? So let me just pull up the code here so I know what I'm torturing you with here, right? So print out using a for loop, square brackets, okay? Then I'll put the code up for the explicit iterator and then try your auto, right? So a whole lot of copy paste can happen in there to help you do that faster. But there's your kind of iterator syntax. And your auto will begin with the dot begin method. So auto q equals vec dot begin while I'm not equal to vec dot end. And see if you can get those things to print out okay. So we'll be looking something like that. Of course, we all know pretty well. And then try that mess right there. Don't forget to dereference Q. So remember, Q is like a pointer. So if you print Q, you're going to get some weird output. I'm trying to remember if it'll even print Q for you. But you want what Q is pointing to, even if it's not really a pointer, or what it's referring to, we could say. And then you can copy paste that thing and just plop the auto in there and life is good. Okay. So our lab 10 this week will require you to use iterators. Okay, lab today you don't have to, but lab 10 will need iterators for that to work because we're going to use a list container which does not support square brackets. Okay. Okay. So there's our kind of 3 ways. Okay. Now, erase and iterators. So erase and iterators go together like peanut butter and jelly, kind of. If you try to erase something from the inside of a vector while you're using dot size, things get really weird really fast because the size is dynamically changing. So your for loop is going to get broken. Okay. So very often we end up using iterators when we're going to do erase. So let's look at this erase method. So here we're saying va.erase from this iterator location, in this case, the very beginning, up to, but not including the end, okay? Which is gonna erase everything, right? Because that stops right at my bumper there, okay? So erase is our first method that requires an iterator to do its job, okay? Rather than numbers, okay? But I could also say erase VB from VB begin to VB begin plus 1. So we're saying erase the 1 and the 23 on that one, okay? So we're using our iterators and relative offsets to describe, how we want to go about doing this. Or erase from the end minus 1 to the end, right? So now it's kind of like Python negative indexing. I could say, hey, I just kind of want to step back from the end by 1 and then erase all the way up to the end. Okay. So there's our erase. Now we won't really need that for our lab today, but that's a really nice one to play around with and get familiar with. Because if you start erasing out of the blue and you haven't done it before, you're probably going to create some pretty nasty bugs. And erase is the best way to actually do that with all of our containers, okay, including vectors. Okay. Questions on that? Okay. All right. So let's talk about our lab today, and we'll get you guys kind of into lab and out of here if you got to go. So we're going to write just a function to make a 2D vector, and it's going to be kind of kooky. So what we want to do is return a copy of a 2D vector. So our function type is going to have a messy return type. It's going to be a vector of int. So it's going to be a 2D vector return type, and that by definition is a copy. So when you send something back from a function, it's going to make a copy of whatever you're returning unless you use the reference type, which we're not going to muck around with on this lab. So we're returning a copy of some 2D vector that we are going to build. So that means we need a local variable of an empty vector in our function. We're going to fill it up, and then we're going to return a copy and be done. And our local variable will go away, okay? So here's our prototype. And notice that the dimensions here is a vector of integers. So what I'm talking about is row 1 has 1 thing, row 2 has 4 things, row 3 has 13 things, right? The next row has 3 things, right? You don't know. So this vector called dimensions is telling you what you're supposed to build, okay? So if your second one has 4 things in it, you want to have 4, 4, 4 in it, right? So the number that we actually put in each row will be the dimension of that row. That's just an easy way for us to error check our code, okay? So build your rows, fill them up with this many things, and put that number in that many times, 13, 3, whatever. Just so it's easy for everybody to kind of see if things are going okay. So here's an example of a whole bunch of things, right? So, and you should return that, right? There's 1 thing, 3 things, 1 thing, 3 things, 5 things, okay? So if you can do this, I think you've got your head fully wrapped around this kind of thing. And also, this is kind of the first time we're starting to kind of see how this thing is actually kind of expanding in our default thing, right? Maybe we've seen that before, but that's the thing. So I'll leave you with that. You can do it either in Pro or the Add Online compiler or Replit. And of course, don't forget your quiz and your homework too. And that's it. So I'll leave you with that, and I'll see you guys on Thursday. We'll talk about the list container. Okay, thank you.